1 and done. Let's go. Hello and welcome back to Differential Equations, section 4.3, Translations and Partial Fractions. We already used partial fractions to solve equations, and now we just, I guess, use them again. So the partial fraction decomposition learned in Calculus 2 and then before that in Pre-Calculus 1 states that you have to break the function, right, apart into multiple fractions by observing the denominator, right, the factorization of the denominator. So what you have are these 4 possible cases that you can set up and then work out the algebra to determine the coefficients you get. So these are the setup. We have something, I'll just call it blah, over x minus c. Now that's the linear term, and the setup for that is a over x minus c. Now we can also have that one squared, in which case the setup is a over x minus c plus b over x minus c squared. And then we can have a quadratic which cannot be factored further, like x squared plus 1. You cannot factor that one. So we will just write it as the quadratic. You can't factor it any further, so the setup for that is ax plus b divided by ax squared plus bx plus c. And the last one is the quadratic that it's, again, not factorable, but it's squared, it's repeated. And you get the same deal like with a repeated. There we go, linear, bx plus c squared. Good. So if you look, there is a great symmetry in this setup. First off, realize that when you have a linear x to the first power, the numerator is just constant. When you have x squared in the denominator, you have linear x. Right? So it looks like that the denominator is always 1 power less. The next part is to realize that for repeated, you keep the x minus c and then x minus c squared. Over there, ax squared plus bx plus c, and then ax squared plus bx plus c squared. So there's a lot of symmetry as you look at these. One crucial point here that students tend to forget is that the partial fractions cannot be done on the problem where the numerator has the greater exponent than denominator. So you have to do the long division, and then when you do the long division, you do partial fractions on the remainder. So say that you're solving, let's use partial fraction in Calc 2. So you're solving integral which says x cubed minus 5x plus 3 divided by x squared plus 1 dx. Now, it should be clear that this is partial fraction. Well, let's go with, that this is, times x over here. There we go. So this is a partial fraction question. But the issue here is that exponent in the numerator is 3, exponent in the denominator is 3, but partial fraction works only if the denominator has the greater exponent. So your job is to actually do the long division first and then deal. So you have to divide x cubed plus 0x squared plus x plus 0. You don't have to put plus 0. Divided into, you keep the placeholders. So x cubed plus 0x squared minus 5x plus 3. So you do the long division first, and once you're done with long division, then you can do. So this is going 1, and then you multiply it back, you get your x cubed plus 0x squared plus x, and then when you subtract all of this, these die, you get negative 6x cubed plus 3. That is your remainder, because x cubed is not going to go into negative 6x. So this problem is 1 plus negative 6x plus 3 divided by x squared plus 1 dx. And now you can unleash partial fraction decomposition upon the term where the exponent in the numerator is greater. So that's generally most of the oversights and trouble that you would make in differential equations if you don't remember that piece from Calc 2. Partial fractions we did last class, so we know how to get the solution. Let's take a look at one example from homework to make sure that that's still with us. Yes?
Did you say that the exponent in the denominator is bigger? I think you said. If
the exponents are the same or numerator is bigger, you can't do the partial fraction until you do the long division. Only when the exponent in the denominator is bigger, you can do partial fraction right away.
I think you said opposite.
All right, so now we can do partial fractions. I'm not going to do it. So now let's take a look at some of these partial fraction problems. Good evening. So the problem 14 says that your f of s is given as 5s minus 4 divided by s cubed minus s squared minus 2s. So your job is to just figure out the inverse Laplace for this, right? Because you go from frequency domain fs back into x of t, or f of t, whatever, f of t. So 5s minus 4, that's a 5, not s. So it's not ss, it's 5s. Minus 4, and then we have s, and then we have s squared minus s minus 2. Can we factor this one? Is this s minus 2 s plus 1? Thank you, Ryan. Brian, oh my God. Ryan. I got the
it was
B.
Brian, you were calling me by the wrong name for the last 3 semesters.
Oh, sorry, Brian.
Yeah.
Yeah, right. I'm so tempted to do Dory now. Can I help you? So let's go. Partial fraction decomposition. So we have the setup. A over s plus b over s minus 2 plus c over s plus 1. Oh, come on. And this needs to be 5s minus 4 over s minus 2, s plus 1. Oh. Now, we cross multiply everywhere where we're missing stuff. So we're missing s squared minus s minus 2. So as squared minus as minus 2a. And then b is missing these two. So plus bs squared plus 1bs. Yep. And then c. So plus cs squared minus 2cs equals to 5s minus 4. All right, so a plus b plus c times s squared plus, and then for s we have negative a plus b minus 2c times s, and then the constant terms minus 2a. Is this it? That's it. Equals to 5s minus 4. So a plus b plus c equals to 0. Minus a plus b minus 2c equals to 5. And negative 2a equals to negative 4. From there we have a is 2. We immediately plug a equals to 2 to both of the other equations. We get b plus c equals negative 2, and then b minus 2c equals to, this is negative 2, 7. If we subtract equations, b minus b is gone, then we get the 3c equals negative 9, c equals to negative 3, and if c is equal to negative 3, b must be 1. Or just find your way through these, and then our partial fraction decomposition, what we get is a 2 over s plus b is 1 over s minus 2, and then plus c, which is negative 3 over s plus 1. Now this is 2 times 1 over s plus 1 over s minus 2 minus 3 times 1 over s plus 1. Do we remember what these inverse Laplace transforms are? They are all e to the, exactly. So 1 over s transforms into t, so we have 2t, and then we have plus e to the, 2t, and then minus 3 e to the, very good. The transformation, not equal, sorry. If you haven't memorized the Laplace transform table yet, you still have 2 weeks, apparently.
Wait, are we getting it on?
There you are. But it's so much cooler if you know it.
Okay.
Now just imagine someone start talking to you. Just put it out there. Laplace transform. All right. Are we ready for the translation property? All right, let's do it. So this is Theorem 1 for this section. So translation means shifting, right? Translation on the x-axis. So Laplace transform exists and right all that stuff. So Laplace transform of e to the at times f of t is equal to f over f of s minus a, and equivalently inverse Laplace of f of s minus a is equal to e to the at f of t. So what does this mean? Shift, right? We know that when you add or subtract values on x, we know this from pre-calculus, hopefully. When you add and subtract values directly from x, you shift things left and right. Now, in Laplace transform, a shift left or right, which is clearly denoted here with minus a, right? So this is the piece which says it's the translation, because you move it a units either left or right, depending on whether a is positive or negative. So s minus a in Laplace transform translates into e to the at times f of t. So that's the Laplace transform for it. And then you have the inverse immediately if you just read it backwards. You can apply inverse Laplace on both sides over here, and then you see that you get the formula on the bottom because Laplace and inverse Laplace cancel. So that takes care of these. So now can we, let's see if I can find an interesting. If it is plus 3, shift to the left 3 units. If it's minus 3, shift to the right 3 units. That's it. All right, so let's take a look at initial value problems. Let's solve 2 of these and then move to the next lecture. So let's start with the vanilla one. 28 x double prime minus 6x prime plus 8x equals to 2. And then initial condition, x equals 0, fx of 0 equals x prime of 0 equals 0. Do you remember transformation of derivatives? Great. Do it.
S squared over S equals minus S of 0.
Yeah, all of those f of zeros are zeros. So that's why I skipped them, right? Because of the initial condition.
So the transformation of 2 is 2?
And maybe we can use capital X of Fs. What happened?
Transformation to the right side is 2?
No. What's the transformation of the...
I don't have a book. So
You don't have book, it's 2 over S.
hey,
So when we transform the equation, we have all of those f of zeros and f prime of zeros, in this case x of 0 and x prime of zeros. They're all zeros because of initial condition, so we don't have to write them. We just write the first term. Now we fish out f of s, and we have s squared minus 6s plus 8 equals to 2 over s. And does this, yeah, minus 2 minus 4. So f of s is 2 over s, s minus 2, s minus 4, right? When you factor it. And now you crank partial fraction decomposition. So I omitted all of the conditions because they're all equal to 0. We transform 2 into 2 over s, and then this one, when you factor it, you get s minus 2, x minus 4. Because they were multiplied on the left-hand side, they become divided on the right-hand side. And now crank partial fraction decomposition same way as we did in the previous example. We good? All right. So we have a over s plus b over s minus 2 plus c over s minus 4 equals to 2 over s, s minus 2, s minus 4. And now we do the multiplication. So we have as squared minus 6as plus 8s plus bs squared minus 4bs plus cs squared minus 2cs equals to 2. So a plus b plus c times s squared plus minus 6a plus 8 minus 2c. No, something is wrong. It's not 8. 8as. Sure, why not? Is it good? You're just a. I had it right. Yes, 8a. Because it's 8. S, A6s. So it's this. It's this over here. Times s everywhere. Times a everywhere. Sorry. So as squared minus 6as plus 8a. Yeah. And then we have a bs squared minus 4bs. Yeah, that's all good. So now I need all s's. So this one minus 4b and minus 2c times s, and then plus 8a equal to 2. So now a plus b plus c equals to 0. Negative 6a minus 4b plus 2c equals to 0, minus 2c, and 8a equals to 2. Well, that's a quarter. Nice. So we have b plus c is equal to a quarter. Divide everywhere by 2 over here. Negative 2. If you divide by negative 2, you have 3a. Is everything good?
I'm just going to read that 8a with 2
This one?
Yeah.
Alright. So now when I divide by negative 2, if I divide by negative 2, this becomes a 3. So 3/4. So negative 3/4 on this side. That's for a. And then this is 2a plus c. There we go. And now I subtract equations. This is not supposed to say 2a, it's supposed to say 2b. So when I subtract equations now, I have, you want negative b? You want bottom minus top or top minus bottom? It doesn't matter. Bottom minus top, sure. 2b minus b is b. C's are dead. It's a negative 1, right?
Wait, isn't it supposed to be b plus c is negative a quarter? If you have a plus b plus c is 0 and a is a quarter and a is a.
Yes. So now it ruins everything over here. It's negative half. And C is a quarter. Thing. We'll get the position of the assistant. Yes. It's okay, it's 4 cents an hour. It's paid position.
I was knighted in my early calculus class.
Knighted?
Because I had to type on the calculator because we had it projected. And so I got knighted.
I'm gonna make you a Jedi Master then. You keep spotting my errors like that? No, not Jedi Master, Jedi Knight.
Yeah.
Jedi Knight. I'm the Master.
I'd rather be a knight.
I'm a Padawan, that's why I'm taking this class at both times.
It takes time. Alright, so we have 1/4 times 1 over s minus 1/2 times 1 over s minus 2, and then plus 1/4 1 over s minus 4. And when you look at, you hit it with the inverse Laplace, you get y, is it y of t? No, x of t. One quarter. No, it's just 1/4. Just 1/4 minus 1/2 e to t plus 1/4 e 4t. There's no t. Did I put a t less?
You did for the other one.
Yeah, it's just 2.
Because if a is equal to 0, then it would have to be 1.
Yeah. Fixed. There we go. Now you can differentiate this twice, plug in differential equation, make sure it works, but it will work. Yeah, go back and fix it. Go back and fix it. There's no t over here. Oh, you did? Right here. Yes. All right, and let's do one spicier example. Ready? Problem 37. X double prime plus 4x prime plus 13x equals to, walk the doors, t e to the negative t, x of 0 equals x prime of 0 equals 0. No, I lied, 2. There you go. Oh, you didn't get me over. Why is that funny? There might be a condition, you know that. No.
Oh, and it's 2 to the n. Okay. Okay, so what did you find that it was?
Well, I have tried. Because this is the last track. But I don't remember how
Wow. Thank you. That's in your answer. Where it's equal.
But I also
You should give her an ultimatum. Like, you do this? Okay. Yeah, now I'm thinking, since that's the case, I'm thinking what to do. No, that one's kind of given.
it's getting big.
Yeah, what do you do? Wait, I was here last week.
But then again,
Group over here, no one. He still up and down.
I have a question. When do you know it's yeah, but this is plus. Yeah. Because that's
Now we're going to have to use that third display.
Wow. This one might be extra crazy. All right, so apparently this one is not nice, right? Oh. You got this? You want a marker? S squared f of s. This should say capital X of s, but minus s x of 0 minus x prime of 0 plus 4 f of s minus 4 x of 0 plus 13 f of s equals, and now we do the transform. So we have to use
Why would you get that minus 4x of 0?
because that term is multiplied by 4, but it's going to be 0 anyway. So yeah, the whole term is 0. Now, what happened?
Talk about all the scholars who do non-parallel. Having Griggs, by the way, Cameron has.
All right, and now we have to use the translation, guys. We have to use translation for this transformation here. We need the Laplace. So for this part, right? We need the Laplace of t e to the negative t. Now, what do you know? We know that the Laplace is given in this formula that we covered earlier. Somewhere. Should be a box around it. Oh, there it is. So you have e to the negative t, so a is negative 1, and then you have the transformation. So a is negative 1 over here, a is negative 1, and you are supposed to get the Laplace transform of s minus a. Maybe I should write it here. So Laplace transform of t, which is your f of t, is 1 over t squared. Sorry, 1 over s squared. But then that s needs to be moved. So it's going to be 1 over s plus 1 squared. I don't know if that makes any sense.
No.
So let's talk. I'm trying to.
It's all
Where?
N factorial.
it's the second function.
And factorial one.
Yeah, the n is
Oh, yeah, it is. But I'm using translation to get the same thing, because what if it's not on the chart and the translation helps? So let's discover. Wow.
so enthusiastic.
Yeah, what if it's not on the chart? Okay, then don't listen. So one more time, we have the Laplace transform of f of t times e to the at is given as f of s minus a. Now, this a that you feed in here and this a that you feed in here is the same a. Now, the transformation of t is 1 over s squared. We are picking up from what we need to transform that a is negative 1. So when you put those two together, the form is 1 over s minus 1, everything squared, which gives us 1 over s plus 1, everything squared. So I hope that you all have s plus 1 squared here. Now we can also use the formula. It says that the Laplace transform, this is a terrible Laplace transform of t to the n e to the at is n factorial over s minus a to the n plus 1. So now we see that n is equal to 1 if you compare the problem, and a is equal to negative 1. So you plug those in here, you get 1 factorial divided by s minus 1 is plus 1, s squared. So you get the same thing. All right.
Now we take it from that.
Yeah, so s squared f of s. This one dies, minus 2. The next one is plus 4 f of s. Then the next one dies. Then we have plus 13 f of s equals 1 over s plus 1 squared. There we go. So now, factor out f of s, and that will give us s squared plus 4. There was supposed to be an s there. 4s plus 13. And then this minus 2 goes to the other side as plus 2. Is this good? Everyone happy? As much as you can be, right? And now fs, which is the solution in frequency domain, is 1 over s plus 1 squared, s squared plus 4s plus 13, plus 2 over s squared plus 4s plus 13. Oh, come on. So this will divide into both terms. So each one gets its own s squared plus 4s plus 13. Now that one is prime. You can't factor. So you actually have to work with it. And this is where you start dreading your life, right? That you are STEM.
So wait, that side gets multiplied just by the s plus 1 squared? Or no?
Which side?
The 2 over s squared plus 4 squared?
Oh no, we can't do partial fraction for this because it's only one. You have to have at least two different factors. You only have one. You do partial fraction here.
Yeah.
Over here we have to use something else.
That's the block stuff?
No, that's for the left one. What do we do for the right one? Evan, what do we do for the right one? We will do the oh god damn. Partial fraction? Now how are you going to use partial fraction on the second one? Let me see.
The only factor that is itself is 1.
We only have one thing here. There's only one factor. You can't use partial fraction there. You have two factors here, and only one here. Can't use partial fraction on one factor.
So what is this? This is law over ax squared plus bx plus c is ax plus b over big AX.
But that's going to be used here, because you have multiple factors in the denominator. When you have this is a separate problem from this one. They're two separate problems. When you only have one factor, you can't use partial fraction decomposition.
Can I show you what I'm confused about?
New mathematics. Yeah, I know.
Like, where's the other factor here? Like, that's not. It's your quote of the day. Because, like, is this supposed to be multiplied by x minus?
No, you have to have multiple of these together in order for partial fraction to work. These are just setups per each, but you can't see partial fraction decomposition can be done if you have x plus 1, x minus 1. You can do partial fraction and then there is something here. You can do partial fraction when you have x minus 1, x squared plus 1. You can do partial fraction, no problem. You cannot do partial fraction if you just have x plus 3, because it's just one term. One factor. There's no other factor to do partial fraction decomposition, because partial fractions means you're getting more fractions. From this, you can't set up other fraction. There's only one, and there is. Yeah, but when you have separated, maybe we can get something out of.
Oh, I was volunteering to do that.
Oh, okay. Completing the square is not your thing. So maybe we can get something from completing the square. Yeah. Let's go. So I'll say partial fractions. And then I will trust you with this one, because you do partial fractions when you go home. Because we did 5,000 partial fractions. What we haven't done is completing the square. And completing the square on s squared plus 4s plus 13 is going to be 4 divided by 2 squared is 4. So, right, you take half of b and square it. So we have s squared plus 4s, and then you have plus 4 minus 4 plus 13. Maybe I can use different color for these, what I call magic numbers here, because they make this work. And now, the completing the square here gives us s plus 2 squared, and then you get plus 9. Plus 9. So now, this problem is transformed into 2 over s plus 2 squared plus 9. Now, we have the structure for k over s squared plus k squared, because that one goes into sine kt. Now, this is extremely similar, but we have to fix it, right? First off, I have issue with k squared and k. This is not 3 and 9, this is 2 and 9. So I have to fix that first. The way I fix that is I need a 3 on top, right? Because this needs to be 3 so that this could be 9. So I need a 3 on top. So I make the 3 on top, but if I multiply by 3, I have to multiply by 1/3 to counter it. So now this problem is transformed into 2/3, and now I have 3 over s plus 2 squared plus 9. All right, so we fixed those k's. The next issue is s, and you have s plus 2. Now, that's the translation principle that we used, and the translation principle says that if you have s minus a, remember, s minus a, well, now we're using the inverse one, right? It goes as times e to that exponent. So this one is now, when I write it again, is going to be s minus negative 2 squared plus 9. So this magic a is negative 2. So the problem is, the inverse Laplace of this is 2/3 e to the negative 2t sine to the 3t. Sine of 3t, sorry. Yes? That's what, yes, that's what the theorem was for. I will go through this argument one more time. Please pay attention. This is, guys, I have to label this as very simple, but it's very convoluted. We're not doing any calculus here, okay? There's zero derivatives, zero integrals. I'm not talking about any high outer space concepts. This is basic algebra. But it's very tricky, and you haven't done anything like this before, so you have to focus and you have to chase these things around. So we'll start from scratch on this problem, and we'll go through all of its aspects, but I want to actually write the convolution, sorry, convolution, that's the next thing we need. I want to write the Laplace, Laplace of e to the at of some function f of t is f of s minus a, and then inverse Laplace of f of s minus a is going to be e to the at and then f of t. Now, the trick that we will be using most of the time is if you see s minus 3, then a is 3, because s is s, minus is minus, and then a is 3. If you have, let's say, s plus 4, well, that you write that as s minus minus 4, because you need to match s with s, minus with minus, and then a is negative 4. So that's a skill that you need. Again, no calculus in that skill. So I just wrote the formula that we are using on the board, so you can quickly pick those things up. So here we start with a differential equation that we can transform, right? And we have initial values on the side. Focus, focus.
So without those initial values, this Laplace of it.
Exactly. If you don't have this, you can't do Laplace. Now, we transform x squared, first three terms, times 4x prime, next two, and then the last one, 13f of s. Right? So we do that transformation. And then we need to do a transformation for t e to the negative t. Now, that t to the n, e to the at, is included on this chart. But it's not included in a chart that I'm providing for the exam. So you cannot bank that you will see this one on the chart as is. But you know this formula, and that is what I worked out here, so you can see that transformation. So we are supposed to Laplace transform t to the first power e to the negative t. What I'm picking up from there is that transformation of t is 1 over s squared, which is on every chart that's provided. And we also pick up that a is negative 1. So now, using our Laplace transform table, simply by comparison, I know that this part here is 1 over s, right? That's your f of t, 1 over s squared. And I know that I need to shift that negative 1. So I write it as it's 1 over s squared, but that s needs to be shifted because we have the form for it. It's shifted negative 1, so minus negative 1, it becomes 1 plus s plus 1 squared. And that's what we have on the right-hand side. Pandora. Yes, it's opposite sign always. It's always opposite sign, yep. Then I used the formula from the chart, which generally is not included on every chart. Then we do a lot of algebra here, combine, move things, and so on. And then we get to the point where we actually have a solution in a frequency domain. Fs equal everything else. So what I did is I divided both sides by the polynomial, trinomial there. I did not solve this part. This part is the basic partial fraction decomposition. And this case will have 4 constants because the setup is a over s plus 1 plus b over s plus 1 squared plus cx plus d over the trinomial. So you would have 4 constants there. It will take some time, but eventually you will get the partial fraction, and then you just pick up for Laplace transform, inverse Laplace transform table. So that part you should not have issue with now after a week of Laplace. The second part is the one that you haven't seen before, where we, as Evan commands, we have to do completing the square. So we complete the square using basic algebra, and then completed the square is placed under 2, right, which is the purple stuff. And then we look at our chart. We have 2 options that would fit this situation. Well, one is wrong. The other one is s over s squared plus k squared. Now, you're remembering that s is a variable for a frequency domain. And what we have is number 2. So it's definitely not that one. Now, this one is cosine, right? Cosine kt. Now, that one is cosine. So we can't use that one because it has s on the top and we have no s. Now, if our partial fraction decomposition somehow worked out and there was s there, then you would have to use cosine and not use sine. So you either have s or you don't have s. And that tells you whether it's sine or cosine. So once we get that it's a sine, we see because of this term here, right? This term here tells us that it's the one that it's shifted. So we are using our formula again. Now we're using for inverse Laplace. But then first I have to make sure, in order for sine to work, that I have k squared and k. If I have 9, which is set in stone, then I must have 3 on top, because formula requires to have k and k squared. So square root of 9 is 3. So that I need that 3 there. But to counter the 3, I have to put 1/3 in front. And I don't need this 2. So I will make that 2/3 as a coefficient in front. And the rest stays as a cosine, but it stays as a shifted cosine. Because, sorry, sine, not cosine. When you look at this formula, this is s squared. And you have s plus 2 squared. So that plus 2 is telling you that the whole thing is shifted. So s plus 2 squared plus 9, you move, separate, right, using the trick where you peel off to get the minus. And you have a is -2, and that -2 goes on the e, because that's where the a is. And f of t is the inverse Laplace of this using just k as the... So now, this problem has, the answer to the entire problem is x of t equals, this is your partial fraction part, which you are going to get at home, plus 2/3 e to the -2t sine 3t, and that will be the answer. Now, if you go back and you look at this question again, you just realize that you can do the constant coefficients on the left, right? You can do your constant coefficients on the left, and then you have the t e to the -t. You can deal with that with undetermined coefficients, right? So there are other ways, but none of the other ways are going to be as short as Laplace transforms. And you don't get to do any calculus in Laplace transforms. This is the reason why engineers, before Mathematica and other solvers, right, love the Laplace. You just get to shovel algebra around and you solve differential equation. No integration, no integrating factor, no derivatives, nothing. Just feed everything in, and out comes the answer. So that concludes 4.3. And now 4.4, we have a few formulas to look at. Not too difficult. There we go. All right. I'll post these so you guys can catch up. 4.4 will be the last section here. So let me restart the stream.